Satellites in the crossfire. Every era leaves traces of its vulnerabilities, and for ours, they orbit silently overhead. There are more than 5,000 functioning satellites circling the Earth, together forming a glittering skeleton of our civilization. Every GPS coordinate, weather model, financial transaction, and global internet signal depends on them. Yet they drift through a radiation landscape that is anything but stable. Our planet's magnetic field is weakening, and that invisible armor now grows thin in places. Above the South Atlantic, a region already infamous to scientists, satellites are entering a firing range of cosmic forces. The South Atlantic Anomaly, once a quiet footnote in geophysical data, has turned into the most closely watched patch of sky on Earth. Here, the magnetic field dips unusually low, so low that energetic particles from the Van Allen belts plunge hundreds of miles closer than anywhere else. Imagine the magnetic shield as a bubble. In this region, the bubble sags inward, allowing space itself to brush our atmosphere. Spacecraft that pass over it experience radiation levels high enough to scramble onboard computers. Engineers liken it to driving through a hailstorm made of a Engineers liken it to driving through a hailstorm made of Engineers liken it to driving through a hailstorm made of energy gunning. Anything driving through a hailstorm made of spacecraft that pass over it again and try to pass over. One company learned that lesson the hard way in February 2025. A batch of newly launched Starlink satellites was lost within 24 hours, not to collision or software error, but to a solar storm that superheated Earth's upper atmosphere and thickened orbital drag. Out of 49 craft, 40 burned up in the sky, streaking as false meteors over the Atlantic. 2 years earlier, Capella Space had seen the same physics claim two of its high-resolution radar satellites when unexpected density increases pushed them out of orbit. These failures weren't flukes. They were demonstrations that even billion-dollar engineering bows the solar weather. The South Atlantic Anomaly complicates matters further. As it widens and drifts, it exposes satellites to repeated bursts of radiation. Circuits that should last 15 years degrade in half that time. Sensitive imaging sensors accumulate dead pixels. Hard drives suffer bit flips that corrupt data. Space agencies monitor these effects constantly. The European Space Agency's swarm mission, which maps the magnetic field itself, must routinely pause instruments when traversing the anomaly to protect detectors from overload. The very satellites studying the field struggle to survive inside its weakest zone. Capella Space's Earth observation satellites felt similar consequences in 2023, when 2 units deorbited prematurely due to the same solar-induced atmospheric swelling that doomed Starlink's fleet. Their engineers redesigned future models with larger propulsion reserves and heat-resistant circuits. Precaution became a new engineering philosophy. Plan every mission as if the Sun and Earth might conspire to twist physics against you. Inside these platforms, radiation's impact begins at the smallest level. High-energy protons barreling through space slice through semiconductors, altering binary states. Zeros become ones, ones become zeros. Computers reboot mid-transmission, cameras capture static. On a single spacecraft, a momentary glitch barely matters, but expand that across constellations managing global internet, navigation, and banking systems, and each flip bit becomes potential chaos multiplied through networks. To mitigate those risks, engineers orchestrate defensive routines. When forecasts predict increased solar activity, operators command satellites into safe mode, rotating panels edge onto the sun, powering down non-essential systems, and waiting. It's a kind of technological hibernation. The spacecraft might appear inert, but is conserving life, anticipating the storm's peak. Afterward, teams reawaken systems, rerun diagnostics, and hope no permanent damage occurred. Every successful reboot is a small resurrection. Still, the pattern concerns researchers. Data from SWARM and NASA's observatories confirm that the anomaly's weak zones have split into 2 lobes, one near South America, another creeping under Africa, the magnetic bruise dividing instead of healing. Satellites passing through experience cumulative hits. Radiation belts that used to stay locked around 25,000 kilometers now dip to barely half that at certain longitudes. It's as though the planet's energy field is breathing unevenly. The interplay between solar weather and magnetic decay turns routine orbital planning into high-stakes choreography. Agency schedule launches at carefully chosen windows when geomagnetic conditions appear calm, yet unpredictability reigns. A CME launch from the Sun yesterday might overtake a slower one emitted days before, merge into a double impact storm. By the time those shock fronts reach us, control rooms may have only hours to react. For low-orbit constellations, that's the interval between continued service and deorbit. These episodes also alter how we perceive the night sky. During the 2025 flare season, photographers captured spectacular auroras as far south as Rome and San Diego, while radar technicians battled strange interference patterns. Every flash of color across suburban skies signaled electronic strain somewhere above. Satellite telemetry lit up with error flags. Single-event burnout, where a transistor permanently fails from a high-energy particle, spiked 20% across multiple fleets. Insurance analysts quietly adjusted risk models afterward. Corporate spreadsheets now include space weather exposure alongside supply chain columns. Even the International Space Station, orbiting barely 400 kilometers up, tightened its shielding protocols. When it passes through the anomaly, astronauts retreat to better protected modules, limiting sensitive experiments. The ISS's orbit intersects the region several times a day, each pass a reminder of our fragile haven's vulnerability. Cosmic rays that the magnetic field once deflected now slice close enough to double radiation dosage for short intervals. Future long-duration missions to Mars will face far greater challenges without magnetospheric protection. Yet all this fragility coexists with progress. Agencies are testing new materials, radiation-hardened alloys, self-healing chips, magnetic feedback shields capable of generating localized bubbles. Private companies explore artificial magnetospheres for satellite clusters, producing miniature deflection fields using electric coils. It's early work, expensive and experimental, but the principle mirrors Earth's own design: fight magnetism with magnetism. For now, lifetimes are trimmed, budgets stretched, and operators learn humility before plasma physics. The NOAA Space Weather Follow-On satellite, launched to the L1 point between Earth and Sun, relays real-time solar wind readings, our early warning buoy in interplanetary seas. Combined with machine learning models, it gives a few precious hours notice before magnetic shock waves reach the planet. It's not much, but it turns panic into procedure. Despite these efforts, the broader picture feels uneasy. We've threaded our civilization through a region of space that's fundamentally reactive, assuming permanence in a variable system. The South Atlantic Anomaly is the physical expression of that assumption cracking. Every new communications satellite, climate monitor, or defense platform adds to the stakes. If the field continues weakening over the next centuries, orbital traffic will inhabit an increasingly hostile shell. Some scientists speculate that in another 1,000 years, maintaining low Earth orbit could require active shielding on every craft, spacecraft with magnetic armor just to exist above the atmosphere. Paradoxically, the more we rely on satellites, the more their misfortunes become invisible from the ground. When your navigation app glitches or a live stream stutters, the cause might not be bandwidth. It might be a proton traveling near light speed punching through circuitry 90,000 kilometers away. The cosmic and the mundane have fused completely. Each new solar outburst forces us to confront a truth as old as the dynamo itself. What happens in the heart of the Earth affects the sky we build above it. The magnetic field emanating from molten iron 2,000 miles down dictates whether satellites thrive or die. Its fading strength transforms orbital mechanics into environmental management. Look up on a clear night and you'll see steady points drifting across the stars, beacons of technology, progress, and dependence. They look calm, but behind that stillness lies constant peril, micro-impacts of radiation, molecular scars in silicon, whispers of the Earth's pulse bleeding into space. The satellites endure, patched and monitored, mirroring our own resilience at ground level. We adapt, as life has always done, to the planet's evolving magnetism. If the field continues to weaken, the boundary between space and Earth will blur further. Solar particles will brush us more often, auroras will wander toward the tropics, and our network sky will flicker like an electronic heartbeat. The world won't end, but it will glow differently. Each passing storm, each spinning compass, each fading satellite signal tells the same story. The ground beneath and the heavens above are parts of one magnetic organism slowly changing shape, reading the planet's pulse. Every few years, a quiet ritual unfolds behind the scenes of modern navigation. Teams of scientists gather around servers crunching magnetic data, and a new version of the world magnetic model is born. To most people, it's an invisible update, a line of code sliding into GPS systems and smartphone apps. But to the researchers maintaining it, this revision is like a cardiac scan for the planet. The model maps the shifting shape of the planet. The model maps the shifting shape here. Magnetic field, where the poles are drifting, how strong the field is, and where anomalies grow. Each line of data records the beat of Earth's inner heart. High above, the European Space Agency's swarm mission keeps watch. 3 identical satellites orbit in a silent triangle. Their sensors attune to subtle magnetic tremors. Launched in 2013, they've charted how the field strength ebbs and flows in real time. Their readings confirm the acceleration of the North Pole's sprint toward Siberia and expose the branching weakness beneath the South Atlantic. Every orbit feels like another pulse check, each variation a new rhythm from the molten ocean far below. For scientists, it's as if the planet finally allowed them to place a stethoscope to its core. But measuring a heartbeat is not the same as predicting it. The Geodynamo that generates the field behaves chaotically, driven by molten iron swirling at thousands of degrees and speeds of kilometers per hour. When computer models simulate that turbulent sea, they rarely evolve the same way twice. Sometimes the magnetic poles wander, sometimes they split, sometimes they stabilize for millennia. Even the most powerful supercomputers can only mimic a semblance of the real thing. The core's swirling geometry defies deterministic forecasts, its weather made of metal. Dozens of research groups attempt to tame that unpredictability. At France's Institut de Physique du Globe, teams feed swarm data into simulations that stretch centuries into the future. Their models aren't prophecy. They're probability maps showing where flow patterns might strengthen or falter. In the United States, geophysicists use seismic tomography, ultrasound for the planet, to infer heat flux patches at the core mantle boundary. These regions act like fingerprints on the dynamo, guiding magnetic energy outward unevenly. When a patch grows hotter or cooler, the field above it responds. Watching those changes is like observing tides in slow motion, waves of molten motion taking centuries to crest. The question everyone asks, are we headed for a reversal? Remains stubbornly unanswered. A few observables hint at possibility. The overall field is weakening, polarity patches are drifting, and reverse flux beneath Africa continues expanding. Yet none of these trends guarantee a flip. History shows many periods when the field faltered and then recovered without reversing. Scientists call those excursions temporary reorganizations that mimic reversals but end prematurely. The planet flirts with chaos, then steadies itself again. Current data could represent another such flirtation, a slow 1,000-year wobble rather than a definitive turn. In a glass wall lab at the British Geological Survey, researchers overlay present-day readings on maps of ancient field lines extracted from lavas. The comparison looks haunting, bright bands of strength fading in similar regions recorded before past excursions. It's tempting to interpret pattern as prophecy, yet even the specialists warn against reading too much. The dynamo's pulses aren't clockwork. They're improvisational jazz, occasionally repeating motifs but never exact melodies. Still, the resonance is familiar enough to make scientists lean closer, wondering if the tune is changing key again. Beyond theory, the technology monitoring this phenomenon has transformed how humanity interacts with Earth. Airliners, drones, submarines all depend on current magnetic models for orientation. When swarm detects a shift, navigational charts update, sometimes nudging airport runways by fractions of a degree. These tiny corrections ripple through global logistics, recalculating flight paths and shipping routes. A magnetic anomaly in the mantle can alter real-world economics half a planet away. It's an extraordinary chain reaction. Molten iron churns, satellites measure, algorithms adjust, and commerce responds, all inside a mechanism most people never realize exists. Recently, new proxies emerge from unexpected sources. The Archaeomagnetic record, traces of magnetism trapped in ancient fire pottery and kiln bricks, reveals snapshots of field intensity over historical timescales. By measuring how iron particles align when clay cooled thousands of years ago, researchers can reconstruct local variations year by year. When those puzzle pieces are combined with modern satellite data, they extend the magnetic timeline into human history. Temples in Mesopotamia, hearths in China, and African smelting sites become data loggers, each one preserving a heartbeat from a different era. This convergence of archaeology, physics, and space science builds a living biography of the field's decline. Charts show jitters that match political epochs entirely by coincidence, an irony not lost on researchers. During the Roman Empire's peak, the field was stronger. By the Renaissance, it had already begun to fade. Now, in the age of satellites and reactors, it continues to wane. The narrative feels almost poetic. As civilization grows more technologically magnetic, the planet's own magnetism diminishes. But correlation doesn't mean consequence, it's simply rhythm. Scientists debate what, if anything, this long descent implies. One camp argues that fluctuations of a few thousand years are ordinary background noise, the dynamo's breathing pattern. Another insists that the present speed of decline, about 5% per century, is historically rapid, suggesting deeper upheaval in core circulation. Both may be partly right. Data from lake sediments and lavas show that some reversals start exactly this way: gradual weakening, drift accelerating, followed by centuries of magnetic chaos before inversion. Yet other weakening episodes stabilized and recovered. From our century-long window, the distinction looks identical. It's like judging the sea's direction from a single ripple. Meanwhile, computational advances are turning these riddles into testable predictions. Supercomputers at NASA and ED Zurich simulate the outer core using equations of magnetohydrodynamics. They compare virtual output with swarms readings, refining flow maps at the boundary between metal and rock. Years of data now reveal a quasi-cyclic oscillation, roughly 2,000 years long in field intensity. If that pulse holds, we may simply be descending toward a trough, not a cliff. The reversal, in that sense, isn't imminent. It's a heartbeat reaching its diastolic pause before the next contraction. Viewing Earth this way changes the narrative from fatalism to physiology. Instead of a planet losing power, picture one adjusting circulation. The magnetic field shields life, yes, but it also responds to life's host. Thermal gradients, mantle plumes, even plate tectonics modulate its rhythm. Volcano chains over Africa and the Pacific vent heat that influences convection below. The crust breathes, the core listens. Every shift above resonates below, completing a system too intertwined to dissect neatly. The emerging insight is humility. After centuries measuring only surface phenomena, weather, quakes, climate, humanity is finally sensing the deep interior in real time. Each update to the World Magnetic Model is a page turned in that chronicle. When the 203 revision arrives, it won't announce apocalypse. It'll note a minor drift here, a subtle weakening there, the quiet murmurs of a system continuing its long conversation with the sun. The planet isn't collapsing, it's speaking in magnetic language, and for the first time, we're fluent enough to listen. From Stone Age fires to orbital platforms, every civilization has lived through this unseen dialogue without noticing the dialogue, without noticing a D. Now instruments relay its every murmur. Satellites charting strengths, sensors mapping current loops, archaeologists decoding ancient imprints. For the first time, we can watch the field move, not just infer that it has. It's like watching time breathe. The heart of Earth beats slowly, measured in millennia, but its pulse reaches us daily through compasses, radio waves, and shields of plasma shimmering at the poles. In the end, reading the planet's pulse isn't about fearing reversal, it's about recognizing continuity. Beneath politics, technology, and economy lies a rhythm older than species, a circulation of molten metal that has outlasted every epoch. Whenever Sworn's instruments hum and the model's numbers shift, that's not catastrophe knocking. It's a deep engine exhaling, adjusting, preparing for another cycle. We're not helpless spectators nor masters of it. We're participants inside its field, living at the tempo of a planet turning its invisible heart toward the future. Living through a magnetic slow motion shift. Imagine waking up in a world where true north never stays still. Not dramatically, no sudden flips or global screams from the planet's heart, just a steady drift so slow you wouldn't notice until your instruments needed recalibrating. That's the world we already inhabit. The magnetic field is shifting beneath everything familiar, not as disaster, but as a slow-motion transformation written on scales longer than any human memory. This is what it means to live through a magnetic transition, centuries of adjustment disguised as normal life. For modern explorers, that adjustment began quietly. Aeronautical charts updated, navigation systems recalibrated, smartphone compasses corrected by software patches. Minor details at first, degrees of drift here, recalibrations there. When the World Magnetic Model revised its data ahead of schedule in 2019, it wasn't treated like breaking news, yet it was a sign. The pace of magnetic change was outrunning expectations. Since then, the North Magnetic Pole's march across the Arctic Ocean has continued unabated, traveling nearly 50 kilometers a year. Each adjustment hides a deeper truth. The engine below is still rewriting its own geometry. Now extend that process over centuries. If the field keeps weakening at its present rate, compasses would need recalibration not every few decades, but every few years. High-altitude routes might shift to avoid zones of inhud. High-altitude routes might shift to avoid zones of inhead, to avoid zones of inhead, avoid zones of inhaben, since the billion for Z. Satellites designed with thicker shielding would orbit a little higher, hugging what remains of the magnetosphere's safe layer. Farmers near polar regions could watch auroras creep south more often, green veils shimmering across places where ancestors never saw them. Life would go on, just beneath a slightly stranger sky. For most people, the changes would feel like folklore. Generations would record brighter auroras, unpredictable compass readings, maybe new myths of dancing ghosts at night. Technology would bridge the gap, faster than imagination could. Magnetic navigation would yield completely to inertial and satellite guidance. Engineers would design chips immune to radiation bursts, grids armored against induced currents. The invisible evolution of Earth's magnetism would become an engineering constant, something to design around, not fear. At the same time, Earth's biosphere would keep recalibrating in its own patient way. Migratory species already adjust to gradual drifts in field intensity. Turtles, birds, fish, each recalibrates through trial and error until the map in their senses realigns with experience. Humans mimic that process technologically. When data shifts, we trace new coordinates. Navigation apps correct themselves, shipping ports re-anchor, power networks evolve redundancies. On every level, life learns to surf the planet's magnetism rather than resist it. Science suggests a full reversal would unfold over several thousand years, a blink to the Earth, countless lifetimes to us. During that period, the field would tangle into complex configurations, forming multiple poles. Some latitudes might find compasses pointing southeast, others toward twin norths, circling different longitudes. It sounds chaotic, yet computers could accommodate these patterns easily. The inconvenience would fall mostly on satellites and power systems, not on daily human life. Civilization would adapt through anticipation rather than panic. Picture an aircraft navigator in the next century consulting not one global magnetic chart, but dozens, each regional, continually refreshed by satellites detecting real-time magnetic lines. Ocean mapping would use electronic bearings derived from live field data, much like weather forecast track storm systems. The phrase magnetic weather could enter the lexicon. Daily updates showing localized drifts, temporary fluctuations, predicted anomalies. It would feel less like apocalypse and more like meteorology for the invisible. This slow metamorphosis may even strengthen our sense of planetary connection. Realizing that the protective field isn't static challenges the illusion of a fixed world. Mountains erode, climates evolve, magnetic poles wander. Stability has always been perspective, not fact. Understanding that helps diffuse the fear of change. The field's weakening doesn't announce an ending. It reminds us that permanence is the rarest condition in nature. Future historians might note how humanity's attitude shifted along with the magnetism. The 20th century treated Earth's core as a mystery locked away. The 21st treats it as an active partner in daily life. School curricula already teach solar storms alongside hurricanes. Children growing up during the next magnetic phase might learn to interpret both. They'll grow accustomed to maps whose north arrows drift slightly each year, just another reminder that the planet breathes. Technologists are preparing accordingly. Space agencies test adaptive shields generating localized magnetic bubbles around spacecraft. Power utilities incorporate solar storm response protocols in grid management software, using AI to preempt surges. Undersea cables gain dynamic filters to neutralize geomagnetically induced voltages. Each solution folds into everyday maintenance, a quiet, endless rehearsal for a magnetosphere in flux. The more we design with variability in mind, the less fragile the system becomes. Meanwhile, artists and philosophers interpret the transition differently. To them, the drifting poles symbolize the mutable nature of truth and orientation. North used to mean certainty, now it embodies change. Exhibitions visualize magnetic field lines as flowing sculptures, reminding audiences that stability isn't the planet's default, it's its pause. Reminding audiences, X-pause. The more it does, the stability isn't the planet's default, it's its pause. And audiences, that stability isn't the planet's default. As its ability is it exhibitions visual stability isn't the planet. In a subtle way, the great reversal becomes cultural as well as geological, a shift from seeking permanence to respecting flow. By the time the field fully reorganizes, whether in 2,000 or 12,000 years, the world will have transformed beyond recognition. Continents may carve new coastlines, languages mutate. Technology unimaginable today would interpret magnetism with ease, but the signal from the core will still rise, modulated through whatever species listens. Magnetic reversals don't erase history. They archive it in stone, encoding orientation for whoever deciphers it next. Within that immense timeline, we remain brief witnesses. Our instruments record the present slope of decline. Our algorithms chart the first tremors of repatterning, yet all of it spans only the overture of a process playing out longer than civilization itself. Comfort is that reversals never equate to extinctions. They're renewals, circulatory resets of the Geodynamo that sustain the magnetic engine for millions of years. Just as the human heart repolarizes between beats, Earth's core shifts polarity to keep its rhythm alive. Back in that opening cockpit, the one where the compass spun, pilots today would find their instruments stable again, recalibrated by updated magnetic models. The memory of that anomaly endures as metaphor, confusion yielding to understanding, instability framed by adaptation. We're learning to live with a restless axis, just as sailors once trusted stars that moved across their seasons. The compass didn't die, it evolved. Every adjustment humanity makes, rewiring power grids, reinforcing satellites, teaching navigation systems to correct themselves, is part of the planet's choreography. The field weakens, we strengthen. The clock of the core ticks differently, we learn its tempo. In the grand balance, no side wins or loses. It's synchronization across millennia. In that sense, Earth's magnetic drift mirrors our own era's transition. Both are experiments in resilience. Civilization survives not by resisting flux, but by folding it into design. The magnetic field isn't failing, it's renegotiating boundaries, showing what endurance truly means. And when the poles finally settle in reverse positions, some distant day when future beings study lava yet to harden, they might find trace of us embedded in the data. Satellites fossilized in orbit, electronics whispering signatures of adaptation. Proof that when the planet changed, we change with it. Because that's what every living system does. It breathes differently to keep breathing at all. The Earth's magnetism is evolving, yes. But Earth's magnetism is evolving, yes. But Earth's magnetism is evolving, yes. But Earth's magnetism, the compass still spins, steadier now, though none of its directions are final. Beneath our feet, the molten engine hums its ancient tune, cycling its charge, readying the next chapter of magnetic time. For a civilization built on electrons and orientation, recognizing that rhythm may be our greatest act of coexistence. The endless reversal. The planet isn't dying, it's resetting its rhythm. Beneath continents and oceans, molten iron shifts polarity in slow waves, and what feels like chaos from our brief human window is simply continuity viewed too close. Earth breathes in magnetic language, exhaling north, inhaling south, a cycle repeating through millions of years. Each field drift we measure is just another heartbeat, another reminder that the ground we treat as stable is pulsing energy written in metal. When compasses spin and auroras bloom over unexpected skies, that's not apocalypse, it's life communicating through physics. The same field that once guided explorers still guards our atmosphere, though thinner now, teaching us humility with every storm. Adaptation, not fear, has always been the core rule here. Species learned it, civilization is learning it, and someday our descendants will navigate a world where north is south, yet orientation remain. All the instruments, satellites, and algorithms watching this shift aren't witnesses to ending, but participants in renewal. The magnetic field's reversal is nature's long-form experiment in endurance, proof that stability is temporary by design. The true anomaly isn't the flip, it's believing the planet should ever stay still. That decision to change polarity is how Earth keeps its heart beating. What we call reversal, it calls breath. If you want to see how solar storms and Earth's pulse connect to our digital future, check out the next story waiting here. Subscribe for more strange truths hidden inside ordinary science, and keep listening. The planet's rhythm is still playing, and we're part of the song.